Welcome to the University of Tolima and Ibagué, the musical capital of Colombia. I want to express our gratitude to the local committee, especially Professor Carlos Sandoval, and the sponsors. Welcome to the 8th Colombian meeting on high energy physics. I hope that the event is of great interest for everyone, and it contributes to high energy physics in Colombia. Our first speaker is Professor John Ellis from King's College London and CERN with the talk Quantized Particle Physics. Welcome, Professor Ellis, and thank you for your collaboration.
Need a bit of help here. Can find the folder. Okay, so it's a pleasure for me to be back in Ibagué. I was here exactly 10 years ago. It's also a pleasure for me to be able to attend in person a COMHEP meeting. I've attended a couple remotely during the pandemic. It's great to meet everybody, old friends, new friends, in person. So, Quo Vadis particle physics. Quo Vadis, here it is here. Adonde vas? Particle physics. So I'm going to introduce, first of all, the status of the standard model as revealed in particular by Ellis experiments, which you'll be hearing more about later on in the meeting. I'll discuss some of the motivations for expecting that there must be physics beyond the standard model. And in particular, there's a lot of motivations from mysteries surrounding the Higgs boson. So you're going to get a dedicated lecture later on about the Higgs boson, so I won't go into great detail. Then I want to present the standard model effective field theory, which I think is an effective way to do a sort of scan over all the LHC measurements to look for new physics. And as one example of a use of the standard model effective field theory, I'll discuss how it might be able to cast some light on the origin of the anomalous measurement of MW by the CDF collaboration. And I'll finish off finally with another anomaly, namely the anomalous magnetic moment of the muon. So you'll be able to refresh your memory of the structure of the standard model by looking at my t-shirt during the meeting. So we've got a bunch of fermionic particles with established SU3, SU2, and U1 quantum numbers. We have a Lagrangian, so the find the button. Yes. So the first line here tells us about the gauge interactions, so generalizations of Maxwell's equations. The second line, how those gauge interactions work on matter fermions. And then we've got the two lines that involve the Higgs boson. How the Higgs boson phi couples to fermions, and down the bottom there, how it gives mass to the W and the Z boson. So as you know, the Standard Model was tested with a precision better than 0.1% by measurements in particular at the LEP accelerator at CERN in the 1990s. And what's happening now is that we're trying to test the two bottom lines of the Standard Model Lagrangian with equal, if not better, precision in experiments at the LHC and elsewhere. So a key role in the Standard Model is played by the mythical Higgs boson. I say mythical because back in the 1960s, when Higgs proposed the existence of this particle, it was regarded as extremely speculative, and the distinguished professors sitting in the front row of the auditorium would sort of shake their heads a bit if you talked about the Higgs boson. But in 1975, together with Mary Gaillard and Dimitri Nanopoulos, we decided, well, the Higgs boson is the real key thing that enables the Standard Model to work, and that is the thing which we have to aim at as a sort of holy grail. But at the time, it was rather distant from experimental possibilities, and so we wrote at the end of our paper, we do not want to encourage big experimental searches for the Higgs boson. Fortunately, our bad advice was not taken, and the LHC was built, large experiments were constructed, and they not only looked for the Higgs boson, but they found it. So here is a moderately recent summary of the measurements at the LHC that bear upon the Standard Model. So on the left, you see various different production processes involving W bosons, Z bosons, top quarks, jets, and so on and so forth. And over on the right-hand side, you see various measurements of the production of the Higgs boson. So as you can see, there are measurements and there are also theoretical predictions. And the good news is that experiments agree with theory. Of course, that's also bad news, because that means that these data don't yet provide us with a good clue as to what might lie beyond the Standard Model, which is the sort of main topic of my talk later on. So, what did we expect for the production of the Higgs boson? So there's various different ways in which it can be produced. The biggest cross-section of the Higgs boson at the LHC is when you collide two gluons, one from each of the colliding protons. And then there are mechanisms for producing the Higgs in association with a heavy W or Z boson, or production in association with a top anti-top pair. You could even have a Higgs produced together with a single top quark. Now we know that the Higgs boson has a mass of about 125 GeV, and if you look at this plot, you see that means that many of those production mechanisms could, in principle, be observed at the LHC, and most of them have been. So we're very fortunate because we're able, with those different production mechanisms, to measure many properties of the Higgs boson. And this is a plot showing the way in which the Higgs boson is expected to decay in the Standard Model. So again, you'll be hearing a lot more about this later on. So the dominant decay mode is the decay into bottom quarks. The ways in which it was discovered Higgs decaying into 2 photons and Higgs decaying into 4 charged leptons, actually a very small fraction of the total Higgs decays. Now, over the past decade, many other decay modes have been observed. Basically, the only one there which has not yet been seen directly is Higgs into 2 gluons, but we do see 2 gluons decaying into Higgs. So that means that, as I already said, we're able to make many measurements of the Higgs boson and its couplings to other particles. So last year was the 10th anniversary of the discovery of the Higgs boson, and the Atlas and CMS experiments published so-called legacy papers giving information on all the measurements that they had made. I'm not going to go in detail through all these. You'll be hearing more about them later on. As promised, many different ways in which the Higgs boson has been observed. Now, the job of the Higgs boson in the standard model is to give masses to the other particles. And that means that its couplings to other particles should be proportional to their masses. And this is a plot taken from the CMS collaboration, where along the horizontal axis, you've got the masses of different particles going from the muon to the top quark. And on the vertical axis, you've got the coupling strength. And the prediction is that the coupling strength should be proportional to the mass at dashed line. And as you can see, that's what the data indicate. And I think this is truly an amazing plot, because you're going over a range of 1,000 in the masses of the particles, and all the way along that line, you get agreement between the standard model and measurements. I might add that there's one decay mode for which evidence was presented recently by Atlas and CMS, which is interesting. It's the decay mode of the Higgs into a Z plus a photon. So this is a process which is not there in the original Lagrangian. It's something that's generated by quantum effects. And so the evidence is not completely solid as yet, but I think this is an interesting possibility for future probes for physics beyond the standard model. And I've got a little picture of Father Christmas in the corner, just to say that this may be a good Christmas present. Okay, so imagine you're a funding agency. And while I've been here, I've been hearing a lot about the funding of particle physics in Columbia. Not all of it good. So imagine you're a funding agency. And they might say, well, you know, you did a fantastic job. You discovered the Higgs boson. You completed the standard model. Congratulations. Go and do something else. Well, my response to that is taken from a poem by T.S. Eliot, who wrote, "To make an end is to make a beginning. The end is where we start from." And the way that I interpret that is, by completing the standard model, we built a solid foundation for exploring more physics, exciting physics, beyond the standard model. And in this connection, I would like to paraphrase James Bond. So, in a film, whenever it was, 25 years ago, he said, "The world is not enough." So, 25 years later, I offer a small update. So I've updated James Bond, I've updated the villain of the movie, and I give you a list of 7 reasons why I think there has to be physics beyond the standard model. The standard model is not enough. And many of those have to do with the Higgs boson. For example, if you do calculations within the standard model, you find that empty space is unstable. The universe will collapse. I'll discuss that in a bit more detail in a moment. Then there's other issues, like, as you know, astrophysicists and cosmologists tell us that most of the matter in the universe is in fact invisible dark matter. We've got matter in the universe, but where did that come from? Why is there matter and not antimatter? The Higgs gives masses to particles through its couplings, but nobody tells you how large those masses are. Those we just take from the experiment. And then there's issues to do with neutrinos, the size of the universe, not to mention quantum gravity. So, for you students out there, there's plenty of Nobel Prizes waiting for you. So let me focus now on the puzzles that have specifically to do with the Higgs boson. So I've extracted from the T-shirt the terms which involve the Higgs boson. So the first one is the coupling of the Higgs boson H to fermions psi. And we don't understand the magnitudes, we don't understand the bizarre pattern of those couplings. This is what is often called the flavor problem. We just don't know. Then we come to the second term, which is the term that gives a mass to the Higgs boson, mu. So we don't understand the magnitude of that either. We don't understand, for example, why that is much less than the scale of gravity, which is 10 to the 19 GeV. And it's more of a problem even than that, because if you try to calculate quantum corrections to the mass, you find that they're quadratically divergent. So, doubly puzzling. Then we've got the quartic coupling of the Higgs. The quartic coupling keeps the Higgs in its place with the appropriate vacuum expectation value, except that it doesn't. When you extrapolate to high scales, you find that the effective potential becomes unstable, and as I already mentioned, the universe will collapse. I also added in there a constant term which corresponds to the vacuum energy, or cosmological constant, whose magnitude is something like 10 to the minus 3 electron volts to the 4th power. Why on earth is it so small but non-zero? No idea. Okay, so let me focus now on the issue related to the magnitude of the Higgs mass. So the issue here is, even if you fix it originally in the Lagrangian, when you calculate quantum effects, you will find that those are quadratically divergent, and so they destabilize the mass of the Higgs. So you have to control those quadratic divergences somehow. For example, you can try to cut them off by postulating the theory known as supersymmetry. Or you can say, well, you were kidding yourselves because you were treating the Higgs boson as being an elementary particle, but maybe it isn't. Maybe it's made out of smaller objects. So many people have tried to construct models of that type, to my mind, unsuccessfully, although that's an effort which is still continuing. Maybe the Higgs is not elementary, maybe it's composite, and if the LHC experiments could prove that, that would be a real revolution. So here are a couple of the diagrams that, when you calculate them, give you enormous corrections to the mass of the Higgs boson. So both those diagrams are proportional to the cutoff lambda squared, but they have opposite sides. So you could imagine that the couplings to the bosons on the right and to the fermions on the left are chosen so that the two quadratic divergences cancel exactly. And actually, that's exactly what happens in the theory of supersymmetry. And it's one of the reasons why despite supersymmetry not yet having been discovered anywhere, I still continue to work on it. I still love Susie, despite the fact that my love for Susie has not yet been requited. Now, supersymmetry could also play a role in stabilizing the universe. So as I commented, if you do calculations in the standard model, you find that the effective potential of the Higgs, which goes up at low scales, is subject to quantum effects which turn it down when you go to high scales. That means that the configuration where we are now, with a small non-zero value of the Higgs, that red dot on the left-hand side, is not the lowest energy state. The lowest energy state is out with a very dense amount of Higgs field. Quantum mechanics will tell you that if there's a lower energy state, you will automatically tunnel through to it. So how can we avoid that? The only way to avoid it is to erect an infinite barrier, which is what happens in supersymmetry. So the instability, the lifetime of the universe, depends sensitively on two parameters of the standard model. So one is the Higgs boson mass, which is on the horizontal axis, and the other one is the mass of the heaviest quark, the top quark, which is on the vertical axis. And if we were down in the bottom right green region, marked stability, there'd be no problem. If we were in the top left red region, instability, the universe would have collapsed in the past. We're in a region where it will collapse, but it will take a long time to collapse. So I'm not going to go through the details of this calculation, but I thought it was useful to at least show the essential formula which comes in, which tells you what is the collapse scale lambda in terms of the mass of the top quark, the mass of the Higgs boson, and also alpha S comes in and plays a role. And so I plugged in the latest values of the top mass and the Higgs boson from the LHC experiments, a recent determination of alpha S, strong coupling, by the Atlas experiment, and the instability scale is somewhere around 10 to the 10, 10 to the 11 GeV. So you may say, well, I don't particularly care that the universe is in principle unstable because humanity is in the process of destroying itself on a much shorter time scale. But I think it is a deep conceptual problem. And as I said, supersymmetry could solve that, and also the Higgs mass stability problem. Supersymmetry also made a successful prediction for the Higgs mass. She said it should be less than 130 GeV, which it is. So the couplings of the Higgs boson should be similar to those in the standard model. It could explain naturalness, help you make grand unified theories, plays a role in string theory, provides dark matter, and could explain the anomaly in the anomalous magnetic moment of the muon. So, lots of good reasons for believing in supersymmetry, but no supersymmetry at the LHC. But I think one has to be a little bit careful in interpreting the results of the experiments. So often the experiments analyze their searches for supersymmetry, making very specific assumptions about the spectrum. So that's done here, for example, in this analysis by Atlas. Those white dashed lines indicate their mass exclusions with a specific assumption about the supersymmetric model. But you can generalize those assumptions. And if you generalize those assumptions, then supersymmetric particles could be lighter than the quoted limit. And the different colors there on the right-hand side tell you that there are models at low mass which escape the LHC constraints. So my message to the LHC experiments is to continue looking. There's lots of corners of supersymmetric parameter space where it could be working. Okay, so I gave a bunch of reasons for thinking that there should be physics beyond the standard model. But, to be honest, there's as many ideas to going beyond the standard model as there are theorists, probably a lot more. So how can one search for new particles if you don't know what you're looking for? So here I take a quotation from the Chinese military strategist Sun Tzu. The direct method may be used. In other words, go out and look for new particles. But indirect methods will be needed to secure victory. Look also for the indirect effects of new particle exchanges. And I'll describe in more detail what I mean in a moment. He went on to say, the direct and the indirect lead on to each other in terms like moving in a circle. He must have been thinking of the LHC and the future circular collider. Okay, so effective field theories. They have a long and glorious history in establishing the standard model. So back in the 1930s, we had an embryonic theory of electrodynamics, which is described by an interaction of dimension 4. We also had a phenomenological description of the weak interactions involving 4 fermions interacting at a point, interaction of dimension 6. Now, there was a lot of discussion for 20 years or so about the precise form of that interaction. Eventually, it was established to be 2 vector-like currents interacting. And then the thought was, well, maybe that interaction between those 2 currents is generated by the exchange of some massive vector particle. And that, of course, motivated looking for theories with massive vector bosons. Enter Higgs, enter the standard model. And I might mention that effective field theories also played a role in establishing the form of the strong interactions, but maybe I won't go into that in detail. So, a powerful method now to look for physics beyond the standard model is just to assume the standard model of Lagrangian is correct. No, I don't have to get a new t-shirt. What's written on the t-shirt is right, okay? But there may be additional interactions between the standard model particles in addition to those on the t-shirt. Maybe I need a bigger t-shirt. So to look for them, you analyze the Higgs data together with electroweak precision data, top data, and you do a global analysis of all possible higher order interactions to see whether there's any evidence for any particular interactions which might give you a hint what physics lies beyond the standard model. So many people have worked on similar analyses. I'm going to present some results from a paper that I wrote almost 3 years ago now, but still, I think it gives you the essential message. So what we did was look at all relevant interactions of dimension 6 under certain assumptions about the behavior of different fermions. And this matrix here sort of lists the various different types of interaction. Some of them contribute to Higgs measurements, some of them contribute to other LHC precision measurements. Some of them could give rise to baryon decay, some of them could give rise to flavor anomalies, and some of them could give rise to anomalous magnetic moments. So I'll be concentrating here on the ones that appear in Higgs and electroweak measurements in the standard model. Now, one of the beauties of this framework is that any individual interaction may contribute to many different physical processes. And so you can put together data from different classes of experiment, which together could constrain operators in a way that individual measurements cannot do. So for example, in the middle there, I have some operator coefficients which contribute to diboson production at the LHC, electric precision observables, Higgs, top physics, and so on. And you do a global analysis to see what are the strongest constraints each can derive on each such interaction. So this is what we did. We analyzed literally hundreds of different measurements, and what did we find? Nothing. We found no significant evidence for physics beyond the standard model. So let me just focus on the top right pictures there. Those tell you what happens if you switch on one operator at a time. And you look to see whether one of those operators has a non-zero coefficient with some high level of significance. And the answer is no. All the operator coefficients are consistent with being zero. So that can in turn be interpreted as telling you about constraints on the possible masses and couplings of particles beyond the standard model. So here we've got a list of all the possible particles that could interact individually with particles in the standard model. And we've got limits on their masses, if they have unit coupling, and we have limits on their couplings if they weigh 1 TeV. And again, nowhere here do you see a significant deviation from the standard model. Then, to the rescue, perhaps, comes CDF. So last year, CDF announced this measurement of the mass of the W, shown here in red, which disagrees apparently highly significantly with the previous measurements, given in blue, and the standard model prediction, given in green. So there's been a lot of theoretical activity trying to understand where such a discrepancy could come from. And in the background, experimentalists have been muttering to themselves, do we really believe the CDF result or not? So one of the uncertainties in the interpretation of the CDF result is the way in which the W boson is produced. And I'm not going to discuss that in detail, but just recently there was a paper by some of the experts in that who analyzed possible uncertainties in the W mass coming from its production mechanism, and at least their analysis could not find an effect big enough to explain the discrepancy between CDF and the other measurements. So let's suspend our disbelief of CDF for a moment. Let's take it at face value and ask where it might come from. And so we analyze this using the standard model effective field theory. Turns out that out of all dimension 6 operators, there's a very limited number that could affect the mass of the W. And here you see the results of our global analysis, now including the new MW measurements. And you switch on the operators one at a time, and circled in red, you see that their coefficients could be non-zero. In fact, if you believe the MW measurement, they have to be non-zero. Of course, there's still the question of whether you believe CDF, but we're suspending our disbelief for a few transparencies. Okay, so let's suppose that CDF is right. Let's suppose that one of those operators has a non-zero coefficient. how could it be generated by some particle beyond the standard model? So we analyze that. There's various different spin zero particles, and vector particles, which could generate those operators. Some of them generated with the wrong sign. So they would not give you a larger value of MW, they give you a smaller value of MW. So you can cross those out. So you're left with relatively few single field extensions of the standard model that could explain MW. And those include a triplet vector boson W, a triplet scalar particle psi, a singlet vector boson B, or singlet with leptons, one neutral and one charged. So I think this is interesting because it forces you to focus on some specific extensions of the standard model which could perhaps explain MW. And at least some of these, I think, could be found at the LHC. For example, the triplet vector boson, possibly the triplet scalar boson. Some of the others are more difficult, but I think it's certainly interesting to push as far as one can the LHC searches for these specific particles. So, Vadis MW. I think the jury is still out concerning the experimental measurement, and I remind you that extraordinary claims require extraordinary evidence, and we're all waiting to hear from the LHC experiments. Nevertheless, we theorists are allowed to speculate, and there are various different extensions of the standard model which could explain CDF measurement and which might provide prospects for detection at the LHC. Vadis SMEF. I've argued that it's a powerful framework for global analyses of LHC and other data. You can look systematically for possible extensions of the standard model and identify possibly interesting BSM scenarios. But I should comment that although the analysis that I presented has been at the level of additional dimension 6 interactions, there could be higher order interactions as well, for example, dimension 8. And I'm not going to discuss that in detail in this talk, but one of my hobbies has been to identify processes at the LHC and elsewhere which might give you a window directly on dimension 8, processes, for example, that don't appear in the standard model and don't appear at dimension 6 either. So I think I've still got a few more minutes. So I'll finish off by discussing the anomalous magnetic moment of the muon and whether it's actually anomalous compared to the standard model. So here's a lovely picture of the magnet for the Fermilab G-2 experiment arriving. And I'm not quite sure whether it's a sunset or a sunrise. From my memory of Fermilab geography, I think that might actually be a sunset. But whether that's a sunset for the standard model or a sunset for our hopes of physics beyond the standard model, I'm not sure. So this story of the anomalous magnetic moment of the muon goes back more than 20 years. So this is taken from an experiment down at Brookhaven in the early 2000s. So they measured the anomalous magnetic moment of the positive and negative muon. They got consistent results, and those results differed from theoretical calculations done using various different sets of data, as I will describe. So in advance of the Fermilab experimental result, a large group of theorists got together and tried to refine the theoretical estimates so that when the Fermilab result came out, we would know whether there was a discrepancy with the standard model or not. So we made a systematic discussion of all the uncertainties. The biggest uncertainty comes from the diagrams written at the bottom left here. These are diagrams where you exchange a virtual photon gamma, which through quantum effects goes to hadrons, and that process is directly related to the cross-section for E plus E minus annihilation to hadrons. So, at least until recently, the preferred way of calculating G minus 2 in the standard model was to measure E plus E minus goes to hadrons, insert your measurements into that diagram. So the dominant contribution from hadrons is when they weigh less than 1 GeV. I mean, the energy scale of a muon is 100 MeV. It's not so sensitive to things which are very, very heavy. So as you can see in those pie charts, the dominant contribution in magnitude, but also in uncertainty, comes from physics around the region of rho and omega. Contribution from relatively high energies is under relatively good control. And so when the Fermilab experiment announced its first results a couple of years ago, their results agreed very well with the previous Brookhaven measurements, but they disagreed very significantly with the standard model calculation based on E plus E minus goes to hadrons data. When I say very significant, the deviation was something like 4 standard deviations. Now, there was already one sort of niggling doubt about this at the time. So, bottom left here, I've got those determinations of G minus 2 based on low energy data. The top, the blue shaded region, is ab initio calculations of G minus 2 using a lattice. Most of them have large errors and they're compatible with the experiment, they're compatible with the low energy data. But there is one, finally I will use this, by the so-called BMW collaboration, which is a result which is relatively precise compared to the other lattice calculations and much closer to the experimental value. So a couple of years ago, when this plot was first produced, people said, well, ho-hum, we're not sure we believe those BMW guys, you know. But subsequently, many other lattice groups have come along and produced numerical results which are quite consistent with BMW and quite different from what you would deduce from the low energy E plus E minus goes to hadrons data. Now, earlier on this year, Fermilab produced a new result. So the new result has bigger statistics, it's got a smaller uncertainty, but the central value is highly consistent with what they'd seen previously, and you still had this big discrepancy, in particular, with the theoretical estimates based on low energy E plus E minus data, although the discrepancy with the lattice was much less. Now, there is an experiment in Novosibirsk called CMD3, which has come out this year with a couple of new papers with updated measurements of the low energy E plus E minus goes to hadrons cross section. So, on the left here, we have their picture of the E plus E minus goes to pi plus pi minus. And over here, they compare their results with previous results. So, the data are scattered all over the place, but when you do a statistical analysis, you find a very significant discrepancy with previous low energy E plus E minus goes to hadrons measurements. If the CMD3 people insert their results into the standard data-driven calculation of G minus 2, you get no significant discrepancy with the standard model. So, it's difficult to evaluate the CMD3 results independently because communication with Novosibirsk has been disrupted by the war in Ukraine. But there is this sort of suspicion that maybe there's an issue with the low energy plus E minus goes to hadron state. So that brings me to the end of my talk. So I have this Titanic summary. So here we have the standard model sailing along happily, and here is the visible matter in the universe, well described by the standard model. Everybody's happy, except that there's the rest of the iceberg, which includes Higgs physics, MW, muon magnetic moment, dark matter, etc. And I sincerely hope and expect that the Titanic will soon be sunk. Thank you.
Thanks, Professor Ellis. We have time for 2 questions, please.
Is there a microphone in your room?
You didn't mention anomalies in physics that start in yes
So you mentioned anomalies in B physics?
Yes.
Yeah. So there's 2 classes of anomalies. One is anomalies in B goes to S, and so sometime there was this apparent violation of lepton universality in B goes to S, E plus E minus, and U plus E minus. But the LHCb collaboration, I think, finally said no, we don't find any anomaly. There is a possible anomaly in B goes to D tau, which is still there as far as I'm aware. And there's also some interest in possible anomaly in decays into neutrinos and antineutrinos. So at the moment I don't think the significances are very high, but they're interesting to follow.
Thank you very much for the talk. That was very enlightening. I was just wondering because, so in effective field theories, if I understood well your presentation, you typically draw couplings at the range of a few percent currently. And I was wondering to which extent experiments must improve their precision. I'm not thinking here about LHC necessarily, but maybe future X factories to actually improve this by a factor 10, 100 to, in the end, maybe see something.
So, to my mind, there's no very clear, sort of landmark or milestone that one should set out to achieve. If I were a believer in composite models of the Higgs, I would say something different, because then I would say those composite models only make sense if the compositeness scale is of the order of a TeV, And so, let's push on to see whether we can observe or exclude some deviation from the standard model at the TV scale. But I'm afraid I'm not a believer in composite models. So I think that we just push ahead and explore.
Okay, thanks again, Professor Ellis.